The Chinese remainder theorem is a theorem about solving simultaneous systems of linear congruences. That is, you're given a series of linear congruences like this, and you're trying to find a single value of x that solves them all. It's not entirely clear how this theorem got its name. There is a problem in an old Chinese math book that hints at problems of this type, but it wasn't called the Chinese remainder theorem until probably sometime in the late 1800s or early 1900s. Regardless of where the name came from, the terminology at this point is standard. We will dive straight into the theorem and then do an example afterward. Theorem. Suppose m1, m2 up to ms are s integers that are pairwise relatively prime. Let capital M be the product of these numbers, and suppose that a1, a2 up to as are integers such that the GCD of ai and mi is 1 for all I. Then this system of congruences has the simultaneous solution that is unique modulo m. We say that a set of numbers is pairwise relatively prime if the GCD of any two of them is equal to 1. To prove this theorem, first notice that each congruence individually has a solution because the GCD of ai and mi is equal to 1. Let Ci be a solution to the ith equation so that ai times Ci is equal to bi mod mi. We now define another collection of numbers ni by ni is equal to capital M over mi. In other words, ni is the product of all the mj except for mi. Notice that ni is relatively prime to mi since all the mi are pairwise relatively prime. This means that there exists another number ni prime such that ni times ni prime is congruent to 1 mod mi. This is the multiplicative inverse of ni. We now have all the terms we need to write down our solution to the simultaneous equation. We will define x0 like this and explicitly show that it works by plugging it in directly. We will substitute for x in the ith equation. Notice that mi divides nj as long as I is not equal to j. This means that when we reduce the expression modulo mi, all but one term will reduce to 0. Notice that ni times ni prime is congruent to 1 modulo mi, and so this expression simplifies a little bit further. Lastly, we need to remember that the Ci were defined to be solutions to the ith congruence, and this completes the proof. To see that this solution is unique modulo m, suppose that y is another solution. Then we have x0 is congruent to Ci mod mi, and y is congruent to Ci mod mi for each I. In other words, for every I, mi must divide x0 minus y. Since the mi are pairwise relatively prime, we know that the product of the mi must also divide the difference. But this means that capital M divides x0 minus y, which shows that there's a unique solution modulo capital M. Since this proof uses a lot of existence claims, it is helpful to look at a numerical example to see how the pieces come together. Example: solve this system of simultaneous congruences. The first step is to solve each equation independently and label the solutions as Ci. If needed, you can use the Euclidean algorithm to do this, but if the numbers are small like these, this can often be done by inspection. Next, we calculate the ni. Recall that ni is the product of all the moduli except for mi. For each of these values, we need to find the inverse modulo mi. Remember that we can reduce these numbers before finding those inverses. We can now build the number x0 using the formula. While this answer is sufficient, it's often helpful to reduce this modulo capital M to get a smaller solution. There are lots of free choices in this process. When calculating the Ci, there are infinitely many solutions. We chose the least positive solution, but it's also possible to choose larger solutions or even negative solutions. The same applies for the choice of the ni prime. For example, you might have noticed that 6 is congruent to negative 1 mod 7, and so you might have taken n2 prime to be negative 1 instead of 6. Fortunately, none of these choices really matter in the end. Regardless of the values you choose, you should end up with a value that works, and it will be congruent to every other value that anyone else could come up with.
Thank you for watching this video. I'm currently dabbling with the idea of creating more videos like these for my classes, and I welcome constructive comments that might help me make better videos in the future.